Now we are going to discuss some of the applications of Gauss law. So the first application is we want to determine the electric field due to an infinitely long charged wire. So for that, this is considered to be an infinitely long straight charged wire. So the dotted lines at the two ends indicate that the length is extending up to infinity. And positive charges are present along the length of the wire. Now these positive charges are distributed uniformly along the length of the wire. So at any portion or any length of the wire, if I will find the ratio of the charge to the length, that will be constant. So at any portion of this long wire, if I find the ratio of the charge to its length, that will be constant. That constant is denoted by the symbol lambda, which is called as linear charge density. So linear charge density of this long wire is denoted by the symbol lambda. So if you cut the wire at any portion and find the ratio of Q by L, it will be a constant. So since it is a charge by length, its unit is coulomb per meter. Okay, students? Now, I want to find the electric field at a point P, for example. For a point P, I will take. So, this is a point P which is at some distance R. Okay, so this distance can be taken as R. At this point, what is the expression for the electric field due to this charged wire? Okay, for that first I will assume the entire length of the wire is considered to be made up of small infinitesimal length. So I will consider a short length of the entire wire. So these are elementary wires. Say this one, this piece is A1 I will take. So this is element A1 and this is element A2. Say for example, if you take 1 meter length of the wire, this 1 meter length of the wire is cut into 1000 parts, means each part of the wire will be equal to 1 millimeter. That is called elementary length of the entire wire. So like that, this infinitely long straight charged wire is assumed to be made up of small elements like A1, A2. I will consider two elements. One is A1 and other one is A2. So now at this point P, what will be the electric field due to this element A1? So I will join the element with the point P, so that the electric field due to this element, positively charged element, no, this one will be EA1. This is the direction of the electric field. Similarly, at the same point P, the electric field due to another element also I will find out. So I will join the element A2 with the point P, so that you will get the electric field at the same point P due to the second element EA2. So these are the two fields acting at this point P. So I will show this point here now. This is the point P. Now EA1 is the electric field at point P due to the positively charged element A1. Similarly, EA2 is the electric field at the point P due to the positively charged element A2. So at the point P, there are two electric fields. Now the resultant of these two electric fields, if you find, means it will be radially outward from the wire. So it will be perpendicular to the length of the wire. So this is the direction of the electric field. Have you understood? Because EA1 and EA2 will be equal in magnitude. Okay. So the resultant of EA1 and EA2 will be acting perpendicular to the length of the wire, or it is radially outward, I can say. Similarly, if you take another point Q here, another point Q. So at this point Q also, if you see there are two electric fields at Q. One is due to the element A1, which is in this direction. So this is EA1. and the other one is due to the element like this, okay. So that this is the direction of EA2. So this is the point Q, and the resultant of these two will be radially outward, perpendicular to the length of this wire. So like this, if you consider the straight conductor like this, if you consider the straight wire like this, the point P is on the right side of the wire on the board, the point Q is on the left side of the wire on the board. Like that, in front, back, at any angle, okay, at any angle, at the same distance, if you take all the points, all these points such as P, Q, R, S, all will lie on a circle. So I am going to show that. So if you join all the points equidistant from the center means, will it be a circle like this? It will be a circle like this. So I will consider two more points. One is here R, the other point is S. So P, Q, R, S, like that several points if you take on the same circle of the same radius, or the electric field will be the same. The magnitude of the electric field will be the same at all points, and that is denoted by E. Okay? Okay. Now, to find the magnitude of this electric field E, I will consider a cylindrical Gaussian surface around the charged wire. Now you see, for example, if you take a wire, whether it is thick wire or thin wire, its shape is cylindrical only. If you cut at any point, the cross section will be circular. The cross section will be circular. So, what will be the ideal imagination of Gaussian surface for this wire? We cannot imagine a sphere. So, for this wire, the shape of the Gaussian surface must be cylindrical. That only is symmetrical with respect to the wire passing through the axis of the cylinder. Okay, students? So, now you can see here, a cylindrical Gaussian surface is imagined around the charged wire. So, you can see that the cylindrical Gaussian surface is having a length of L and a radius of R, and in that Gaussian surface, namely the cylindrical Gaussian surface, how much quantity of charge is enclosed? That is Q. Okay, students? So, if you divide the quantity of charge Q by the length of the cylinder L, that must be a constant. What is the name of the constant? It is linear charge density, and that is denoted by the symbol lambda. So, lambda is equal to, so lambda is now equal to Q divided by L, or Q is now equal to lambda into L. This is equation 1. Okay, students, have you understood? So, Q, the charge enclosed. Q is the charge enclosed by the cylindrical Gaussian surface which we have taken, and it is found to be the product of lambda into L. This is equation 1. Okay. Now you tell me how many surfaces are there for a cylinder. Imagine a cylindrical drum. There will be a top face. Okay. That is circular. And there will be a bottom face. That is also circular. And there is a lateral surface, the curved surface area. There are 3 surfaces. So I am going to consider the 3 surfaces. In all the 3 surfaces, I will find out the direction of electric field and the direction of the area vector. Okay, fine. Now, you see, this is the direction of the electric field due to the charged wire. At every point like this, the direction of the electric field will be radially outward. That is perpendicular to the length of the wire, and it is directed outwards. So, I will consider here at this point, at any point on this lateral surface. So, this is the direction of the electric field. This is the direction of the electric field vector. Okay, students? Similarly, on the entire lateral surface, I will consider a small elementary area only. A portion of the total surface area is called elementary area. And elementary area is denoted by the symbol dA vector. So, I will consider a small elementary area like this on the lateral surface. So, the normal drawn to the elementary area. The normal drawn to the elementary area will give you the direction of the area vector. Okay, now you see the direction of the electric field is outward, and the direction of the area vector, elementary area vector dA also is along the direction of E. So what must be the angle between E vector and dA vector on the lateral surface at any point? It must be 0. So I will write here below this, theta is equal to 0 degree. This point have you understood? So at any point, not only at this point, if you take any point on the lateral surface, the direction of the electric field and the direction of the elementary area vector dA, both will be same. Therefore, theta, the angle between the two vectors, will be equal to 0 degree. Okay, students. Now I will take the top surface, which is circular in shape. The top surface. So the top surface, I will take a small elementary area like this. A small elementary area like this, dA. So the direction of the elementary area, you have to draw a normal to this dA. So this is the direction of a dA vector. But you see that the positive charge, due to the positive charge, the direction of the electric field will be still perpendicular to the length of the wire. Can you see that? The direction of the electric field and the direction of the area vector are perpendicular to each other. So what is the theta here? In this case, theta is equal to what? 90 degree. So the third surface. In the third surface also, you take one small area dA. So you take a normal, okay, draw a normal to the bottom surface, and this will give you the direction of the elementary area vector dA. But still, due to the positive charge on this wire, the direction of the electric field is outward, so that the angle between dA vector and E vector at the bottom surface also is 90 degree. Okay, students? Okay. Now, from Gauss law, the total flux of the electric field, that means the electric flux through the lateral surface or the curved surface plus the flux passing through the top surface plus bottom surface, the total flux passing through the entire closed surface must be equal to 1 by epsilon naught times the charge enclosed. Okay. Now I am going to write from Gauss law. Okay. From Gauss law. The statement of Gauss law in mathematical form. Total flux phi is equal to Q by epsilon naught. Okay. Q divided by epsilon naught. So now what is the total flux here? It is a closed integral E dot dA. E dot dA. Now this closed integral E dot dA must be taken for how many surfaces here? The Gaussian surface is a combination of 3 surfaces now. 2 circular, one at the top and other one at the bottom, and one is curved lateral surface. So we have to find this closed integral, that is E dot dA for 3 surfaces. So I will write. So this is written as 3 terms. So this is E dot dA. Okay. One is for the curved surface. So this is for the curved surface. This is for the top surface. And the third term is for the bottom surface. E dot dA for the bottom surface. So the first one is for the curved surface. This is top and this is the bottom surface. Now this is equal to, that is a closed integral E dA into cos 0 plus closed integral E into dA into cos 90. Okay, cos 90 is 0 plus closed integral E into dA into cos 90. Once again it is equal to 0. So here these two terms get cancelled because cos 90 is equal to 0. And I told you that the direction of this electric field will be perpendicular to the length of the wire in all the directions, and if you join all the points equidistant from the center, the locus of all the points will be a circle of radius r. Okay, students? Therefore, on this circle, at every point such as P, Q, R, S, which are at a distance r from the center, the electric field will have the same magnitude. So, I will take this E outside. So, this is equal to E into closed integral dA. This is equal to E. What is the closed integral of dA for the curved surface? This lateral surface is the curved surface. On this a small area dA I have taken. If you add all such elementary areas, the total lateral surface area you will get. So this dA, this integral of dA is equal to the lateral surface area. Okay, students, the lateral surface area only you have to substitute here. So this is equal to E into the lateral surface area is 2 pi r into L. Is it not that? 2 pi r into L. So that lateral surface area, imagine if it is cut and opened, it will become a rectangle. So that the length is 2 pi r and the width is L. So 2 pi r into L. Okay, so this is therefore phi E is equal to E into 2 pi r into L. So this is equation 2. Now already equation 1 we have. What is the quantity of charge enclosed by this cylindrical Gaussian surface? Q. Is it not? So Q is equal to lambda into L is equation 1. So now we are going to substitute phi E is equal to E into 2 pi r into L and Q equal to lambda into L in the Gauss law. Okay, students, this is the Gauss law. So I am going to substitute here instead of phi E equation 2, instead of Q equation 1 I am going to substitute. Therefore, now E into 2 pi r into L, okay, this is equal to lambda into L divided by epsilon naught, because Q is equal to lambda L. So Q by epsilon naught means lambda L by epsilon naught. Okay. Now which term is getting cancelled? You see here L is getting cancelled on both sides. Now we want expression for only E, is it not? So we will write therefore E is now equal to this 2 pi r is coming in the denominator. So this is a lambda divided by 2 pi epsilon naught into r. So this is the magnitude. This is the magnitude of the electric field. Okay, students. So you will see that E is inversely proportional to R. As R increases here, as the distance R increases, so you are going away from the wire means what will happen at far distance means the field decreases. As R increases means E decreases. So E is inversely proportional to R. This is only scalar form I have written. In vector form means you can write E vector is equal to lambda divided by 2 pi epsilon naught into r cap, where r cap is a unit vector along the direction of r. Like that also we can write. Okay, students. So this is the expression for the electric field due to infinitely long straight charged wire. What kind of charge is present in this wire which we have considered is positive. Therefore, what should be the direction of this field? It should be radially outward. So direction is that is direction of E is radially outward. Okay. Suppose if you take negatively charged wire in place of positively charged wire, if you take a negatively charged wire means then the direction of E will be radially inward. Okay, students, have you understood? Okay, fine.